Let's look at how we can use Prim's algorithm to find the minimum spanning tree. So Prim's algorithm tells us that we should start with any node, anywhere we want. We're going to start at D. It then tells us to add the shortest arc from any node that's already part of our network. Currently we only have D in our network, so the shortest arc or edge from D is DC. So let's write down that we've added DC. It's always a good idea as well to add the arc to your network, because the next stage of the algorithm, it will be helpful if you've got something there, preferably in a different colour, that reminds you what's already part of your tree. Okay, so we've added D and D to C, and now we need to find the next shortest arc, which is connected to our tree. That means we can select any arc which is connected to either D or C now, as D and C are both part of our network. Inspecting those, we see that BC is the next shortest. So we can now add BC. And we continue to do this, each time trying to add the shortest arc to our network. Again, DF, to our tree, sorry. Once we've added DF, remember, we don't have to go from the node we've just added. We look at the shortest, for the shortest arc, which is connected to any part of our tree currently. Having added DF, we do the same again. Where is the shortest arc connected to what we currently have in our tree? That will be AF. Okay, now we run into a slight problem. The next shortest node that I would have to add is A to B. However, AB, if I were to add that, would create a closed loop. There would be a way of starting at B, travelling around my, well, it's not a tree, around my network that I'm building, and I could arrive back at B. So that means that Prim's algorithm stops you adding that node, that arc. I can only add the shortest arc if it doesn't create a cycle. Remember, we're looking for a minimum spanning tree. A tree cannot contain a cycle. Okay, so I don't add that one. I look for the next shortest. The next shortest one is 36. 36 would also create a closed cycle. I could go C, D, F, A, back to C. So I can't add that one either. The next one that I look to add is D to E, this 38 here. Even though it's not the shortest arc, it's the shortest arc which doesn't create a cycle. So I add that to my network, and now I stop. I don't need to check whether that one will create a loop. I can see that I now have a spanning tree. Every single node in my network is part of my spanning tree, and I've done it with the shortest possible length. So if I make a note of what those lengths were, do this before, it makes it a lot easier. You don't need to waste time doing what I'm doing now. I can then add all of those numbers together and I'll get the minimum spanning tree's weight. So bear with me one moment. 50, 70, I think that adds up to 90. My arithmetic's terrible though, so I apologise if that's wrong. But that's how we can get a minimum spanning tree. Remember, a tree doesn't contain a cycle, and a spanning tree visits every node on the network and also doesn't contain a cycle. A minimum spanning tree visits every node on the network without creating a cycle, and it does it with the minimum possible weight.